R2 stands for pairs of real numbers. We can add pairs of real numbers just like we've been adding matrices and vectors, because a pair of real numbers is just a vector with two components. And we can multiply by a scalar, and I want to show you a couple things about how adding vectors in R2 and multiplying by scalars is just like adding real numbers and multiplying real numbers. This lesson should go down really easy because it's very basic material. So let's look at three ordered pairs, three elements of R2. 1, 3, 2, 2, and 2, 0. So if we add these together, of course we get 1 plus 2 plus 2 is 5, and 3 plus 2 plus 0 is 5. Let's do this graphically. Let's say this is the origin right here. So 1, 3, we could draw as an arrow there from the origin to the point 1, 3. And then 2, 2 is going 2 more steps to the right, 2 steps up. 2, 0 is going 2 steps to the right and 0 steps up. 5, 5 is going 1, 2, 3, 4, 5 steps over, 1, 2, 3, 4, 5 steps up. So, of course, we get to the same spot either by going 5, 5 or by going 1, 3 and then 2, 2 and then 2, 0. Now what if we did the sum 1, 3 plus 2, 2 first and then added 2, 0 afterward? So then we have, this part is 3, 5. So 1, 2, 3, 5 would be going up there. And then add 2, 0 and we get to the same place. So that's 5, 5 also. And if we add 2, 2 plus 1, 3 first and then 2, 0 afterward, well 2, 2 plus 1, 3, well then we're going up to this same point. So this is still 3, 5, and then we add 2, 0 to that and we get 5, 5 again. 2, 0. And if we put parentheses somewhere else, let's say 1, 3, and then we went 2, 2 plus 2, 0. So 1, 3, and then 4, 2 more. So then we go to 1, 3, and then 1, 2, 3, 4, 1, 2. Again, we get to 5, 5. Now, none of this should be too surprising because all we're doing is changing the order of numbers and changing where we put parentheses. And we know that if we have real numbers a, b, and c, then a plus b plus c is equal to a plus b in parentheses plus c, which is equal to a plus b plus c in parentheses, and we could even change the order of the numbers here. Those are all the same thing. And when we observe that these same rules hold for pairs of real numbers, it's because they're holding for the first real numbers and they're holding for the second real numbers separately. No, similar things work with scalar multiplication. Let's look at let's look at 1, 3. And if we multiply this by 2, we get 2, 6. So that's like going 1, 3 and then another 1, 3 to get to 2, 6. If we write 2 plus 1 times 1, 3, so that's just 3, of course. That's 3 times 1, 3, which is 3, 9. So I go up another 1, 3. Sorry if I went off the board. And that's the same thing as 2 times 1, 3 plus 1 times 1, 3. That is 2, 6 plus 1, 3 equals 3, 9. So I'm using the distributive law here. 2 times that plus 1 times that is the same as 3 times that. And that works just because here we're multiplying. A plus B times C equals AC plus BC. And I'm really just doing that with the first component here in 1, 3 and then the second component separately. So since those are both real numbers, then the distributive property of real numbers works. Now what if I did 2 times 1, 3 plus 2, 2? Now 1, 3 plus 2, 2 is 3, 5. So we get 6, 10. And we could also do this separately. 2 times 1, 3 plus 2 times 2, 2 equals 2, 6 plus 4, 4, which is 6, 10. Again, just using the distributive rule, this time it looked a little bit more like A times B plus C equals AB plus AC. And the reason it works for pairs of real numbers is because it works for the first components and the second components separately. So I'm just using the distributive property of real numbers twice. Once in the first component, once in the second component. Also, let's look at the fact that if we, let's say we go 4, 2, to use a place I haven't used before, 4, 2. If we want to get back to the origin from there, well, we go -4, -2. So we went to the right 4 and up 2. So we go to the left 4 and down 2 to get back to the origin. So no matter where we go, we can go back again. If 4 and 2 are real numbers, then their opposites are real numbers. And that's just because for every real number A being a real number implies that -A is a real number too. So whatever you do with adding, you can undo with adding also. So I feel like I haven't said much because I'm just reviewing ordinary arithmetic on real numbers. The only difference is I'm doing it 2 real numbers at a time instead of 1 real number at a time. But all the rules still apply because they apply to the first component of these ordered pairs and they apply to the second component of these ordered pairs. The end.